Okay, welcome back to the Neuro Symbolic Channel. In this video, we will give an overview of results of our recent work on error detection and correction rules for metacognitive AI. And this will include a couple of papers. One is our really recent paper accepted to CIKM 24 on error detection and constraint recovery for hierarchical multi-label classification. And the other is a paper we have talked about before on the channel that is available as an archive preprint. And so, some of the ideas in the preprint actually, set the stage for the CIKM paper. And if you're going to be at CIKM in October 24, I'll be there, as well as my student Josh, and happy to answer any questions in person or just talk shop. So anyway, the whole idea of metacognition is awareness and understanding of one's own thought processes. And so if you can think about as a human employing an ML system, over time you're going to notice when it fails for your specific operational case, because any operational case is going to differ from how it was trained, the data that was used for training. And so as a human, you'll probably notice when it works differently, and you'll say, hey, it doesn't work well when there's this kind of a shadow for my vision model, or it doesn't work well for this movement trajectory classification when the vehicle's moving faster than it should. And applications of this deal with identifying these failures, and we had a really tragic thing happen at the end of 2023 where a vision model mistook a man for a box in Korea, which led to his death by a robot. And so how do you overcome these errors? Well, a lot of this goes back to characteristics of the environment. And as I mentioned at the beginning, when you train an ML model, these environmental assumptions are kind of baked in. And really the idea with this approach to metacognition is to figure out, are there certain conditions that cause assumptions to break, and can we maybe even fix the errors in those conditions? And of course, a lot of the work that I do is funded by the DoD, so we're really interested in some of these problems that are relevant to the military, such as ISR. Okay, so we gave enough of the intuition. We don't necessarily want to have a knowledge base, although you potentially could with this approach. Not trying to change the perceptual model. We want to sort of treat those weights as frozen, but we want to be able to fully explain the errors and then adjust the perceptual model, but not actually change it because you don't have access. And we have a logical language where you have this omega symbol. We're just using it as a generic constant symbol in the logic. This represents a sample. You have a bunch of conditions, and we're going to pick from these conditions. So condition J, omega means omega has condition J is true for omega. Pred I means that your model predicted label I for omega. And then we have these two extrinsic predicates, error I omega, which means the model made a mistake assigning label I, and correction J omega, meaning that the correct label really should be J. And so having two types of rules, we have this detection rule, and what this is saying is that if one of the conditions in set DCI is met and the model predicted label I, then there's an error. Now, the key here is finding that set DCI, and that's what we're going to learn from data and what follows. And then likewise for correction, the rule looks a little bit different, because now you have to consider the condition and the class that the model assigned as a pair. So you have these things, we call them condition class pairs. So we have a set of them, CCI. This is what you need to learn to have this type of rule. And if you have one of these condition class pairs is true, then the correct label should be I. Notice the pred and the correct and predicates are for different labels here. Okay, So how do you learn these rules? Well, the idea is to first learn detection rules. So you could think of this as erasing labels, and we do this with some combinatorial optimization. And then once you erase those labels, you can then learn correction rules. And the reason you want to do this in this order is if you go ahead first and learn correction rules, the optimization problem becomes more difficult because you're changing precision and recall of two classes, where if you do detection first and you erase labels that you think are wrong, now in both cases you really only have to worry about optimizing metrics with respect to one of the labels, because in the second step you're only correcting things that have previously been erased. And so we talked about before on the channel, but we'll go over it quickly here. LRCN is a model for is a state-of-the-art model for predicting or classifying the type of movement in a GPS trace, walking, car, train, etc. But it can get confused between similar trajectories. So we wanted to learn some EDCR rules to correct this. And first, just kind of showing, one class, we have this parameter epsilon, which is the bound on the amount of recall that you can lose, and this is under the assumption that there's similarities in data distribution. And this is because in the first step of learning the detection rules, if you pick labels well, you can do it in a way where you can push precision to go up. You can also accidentally cause precision to go down, but we can do this thoughtfully to make precision go up. But when you erase labels, your recall is either going to stay the same or go down for a given label. So unless you can erase the labels perfectly, which in the real world you're not going to be able to do, you're going to have some reduction in recall, and we have that set as a hyperparameter. Now we outperform this theoretical guarantee because we're not just erasing, but we're also relabeling. Now what's key to note here is these results that we had, this was a multi-class problem. We just show one of the classes here, and in the paper you can see all the results. But in general, they all look something like this. But you also got to understand too that this is EDCR rules trained on the same data that the model is trained on. So even when we do that, you may notice here we get a little bump in F1. So we're able to squeeze out some more performance out of the same data by adding these EDCR rules. Now we also did experiments where we removed data with certain class labels from training, and so now you have a few classes and tests that are unseen. And just training EDCR rules on the same training data, we get a fairly significant bump in accuracy, something like in the neighborhood of 3%. And that's because now the model can see when it's being wrong. And we can add additional samples to train rules in sort of a few shot case, and we can start to approach performance that we would have had with a fully trained neural model, which is the dashed line that hovers around 0.75 there. Now looking at our next use case for the second paper, the CICAM paper, we were inspired by multi-class classification with hierarchical labels. So you see in this military example, you have something like a T-72 is a specific kind of tank, and tank is a general category. Whereas BMP, you see it kind of has tracks like a tank, but it's not a tank, it's actually an infantry fighting vehicle. And so you have to differentiate between coarse grain and fine grain labels. And we want to do this in the case where we assume that you don't know the hierarchy ahead of time. Because how, can you just make these corrections without knowing the hierarchy, and then maybe even learn something about the hierarchy from the errors? And so, yeah, I just kind of stated the stuff on this slide. And, related work, we're not going to belabor that here, but it's a lot of the stuff you've seen on the channel, and there's, of course, a lot of classic work on rule learning and ILP. Okay, so going back to our detection rule, which is what we're primarily going to use here, the idea is you have these conditions, and in the other work, conditions would come from domain knowledge or another model. Here we're going to have the conditions come from a different level of granularity of the classes. So if you're predicting something, say, at tank, then the conditions are going to be things like, is it a T72? Is it a T64? Is it a BMP? And based on the slide we showed, if it's saying it's a BMP and it's a tank, that's the kind of rule we think will result in an error. Now, we're not making that determination. We're going to let our training algorithm do that for us. And so these are some examples of what they look like. These are actually learned from data. And we kind of wrote it in this way because you could see YF is the set of labels minus the ones that are listed there on the slide. And it's minus because we wanted to show the reader that, hey, look, it's looking at tank, and it's looking at things that are not a T62 or T72 or T90. Those are all specific models of tanks. So it was able to find that if it wasn't finding a tank at the fine grain and tank at the coarse grain, then this was an error. And the other ones can be read similarly. Also notice the bottom two rules. Now the fine grain is the primary thing, and the coarse grain is the condition used to correct. So okay, first let's look at using this as just a simple way to detect errors, and we can treat finding an error as a binary classification problem, and we can compute accuracy in F1 for the class that something, our algorithm said that the model was in error when it made a determination on the test set. And we look at three methods. So first we look at just training a neural network doing this using, same kind of vision transformer architecture, and this is inspired by some prior work, in particular by Daftry, who uses neural models as failure predictors. The second one, det rule learn, this was from the previous paper I showed at the beginning, and then we came up with a new version to detect errors, train rules to detect errors, and this is by optimizing the error F1, and that seems to do better than the other two, and in some cases by a significant margin. We're beating the neural model by 10% in some cases, so that's kind of neat. And the neural model's not that bad, to be honest, so it's a good result. Okay, so we look at this error scores, and we look at what happens when we start inducing noise into the data that we're training the rules on. But we look at one other metric here, and that's that dashed line. That's really important. And this dashed line, let's see if I can get a laser pointer here. This dashed line is an F1 score, because if you remember on the earlier slide, we gave you some intuition as to how these error rules can be translated into constraints. So we saw that by looking at what was not in the set of error-causing conditions, that we could say, hey, maybe those are types of tanks, or specific tanks for rules going the other way. So we could look at an F1 score on those constraints compared to a ground truth set of constraints that we curated but didn't use in our algorithm. And so we really get pretty good F1 results for finding the constraints, hovering everywhere from mid 70s to low 90s, and then it degrades rather gracefully with noise. We're going down to around 70 with open image, and we go down to around a little bit like 65%, 63% with ImageNet and the military vehicles. So we got pretty consistent results across three data sets, in both in terms of error accuracy and the F1 of these constraints that we recovered. So okay, we got ability to detect errors, we got constraints. What about correcting? Well, rather than using our correction rules like we did last time, since we actually recovered the constraints, for those of you who are fans of the channel, you probably know a lot about logic tensor networks. And this is what we did here. We just took those constraints and we plopped them into the logic tensor network loss function, because it's a logical constraint at this point. So why not? And bear in mind, there was, we're using this purely learned from the data, and we then go back and we retrain the model, now with this new loss function that has our logical constraints, so same training data, so no new data was discovered yet. and we get a pretty sizable improvement in accuracy across the board for the classes. So military vehicles, that's like looking like 8%. The other data sets you're looking at like 1 to 3%, depending what it is. And the reason why, you could see in the last column, these are the number of inconsistencies in the solution. So with military vehicles, we dropped from 126 to 87. So many of those inconsistencies lead to errors. Now, we had the least performance improvement when we did this with ImageNet, but notice it already had a lot lower inconsistencies than the other two. ImageNet, training the vision transformer, we had a 1.19% inconsistency. We dropped it down to 1.05, but it was probably harder for the model to drive it down. It was already had most of the things adhering to inconsistencies, or to the consistent organization of labels, just by virtue of the training data. OpenImage, we had a larger amount of inconsistencies, and again, it was able to drive it down by about a third. Now, bear in mind, if again you're a logic tensor network fan, you probably know that, hey, there's this hyperparameter beta that you can use to trade off between the inconsistency loss and the error loss, and so you can actually set beta to be much more biased, to have more consistent results, even if it's at the expense of accuracy. So you could have everything strictly adhere to constraints, or come close to it, but you're going to lose a bunch of accuracy, and actually what's called reasoning shortcuts will probably start to emerge at that point. Here what we did is we actually trained for a beta parameter that gave us optimal results, and that's what you see here. So this is based on our setup, this is sort of the best trade-off we could get. Anyway, just to wrap up, we have a bunch of papers of interest. This was actually part of a larger deck, and we'll publish that slideshow of the full presentation from the AI workshop at Embry-Riddle and Prescott. But the key papers are our CIKM paper with my student Josh, and then the error detection and correction for movement trajectories that was done by Bu and Shi. And again, as usual, this work is made possible by many great sponsors. All right, well, that's it for this. Thanks again for tuning in, and feel free to like and subscribe. Take care.